Chapter 8, Anatomy of Anterior Chamber and Drainage Angle, from Wolff's Anatomy, 8th edition, page number 294, part 5. Endothelial lining, inner wall. For many years, there was controversy over whether there was or was not an open communication between the anterior chamber and the canal of Schlemm. It is now generally considered that the vacuolar configurations of the endothelium provide a mechanism for direct communication between the extracellular spaces of the trabecular zone and the canal of Schlemm, and are probably the major route for the entry of aqueous into the canal. This concept has been developed over a number of years by studies employing light and electron microscopy, morphometric and tracer techniques. Lining. Schlemm's canal is lined by a single layer of spindle-shaped endothelial cells oriented parallel to its circumference. These are clearly demonstrated by scanning electron microscopy. In the inner wall, there are 40 to 120 micrometer long, 4 to 12 micrometer wide, and are 0.2 micrometer thick. They are connected by poorly defined tight junctions and maculae adherenti, and by occasional gap junctions with cells of the pericanalicular tissue. The junctions occupy only a small area of the cell membrane and do not prevent the passage of leukocytes or macrophages across the intercellular space. The luminal surface of the cells exhibits sparse microvilli. The cytoplasm shows numerous free ribosomes and microfilaments, and also many pinocytotic vesicles. Giant vacuoles. The most prominent feature of the inner wall of the canal of Schlemm are the giant vacuoles. These are invaginations which are generally globular in profile on meridional sections as revealed by transmission electron microscopy. The vacuoles measure from 4 to 6 micrometer in width and up to 25 micrometer in length, and usually are oriented along the long axis of the cell. It is thought that they arise by invagination of the basal plasma lemma of the endothelial cells, thus providing access for aqueous humor in the pericanalicular region. A smaller proportion of the vacuoles also communicate with the canal of Schlemm via luminal opening or pore by which a transcellular channel may be formed. The pore aperture may be up to 2.5 micrometer in diameter, while the basal invagination may be up to 4 micrometer wide. It has been calculated that at any given instant, 2% of the total population of vacuoles are at the stage of transcellular channels, and this number could account for the observed rate of aqueous outflow in normal eyes. The suggestion that pore frequency is greater in the nasal quadrant of the canal was not borne out by. Fraser studies have shown that materials of varying diameter may pass through transcellular channels from the anterior chamber into the canal of Schlemm. This has been demonstrated using thorotrust, ferritin, gold, and horseradish peroxidase. Not all vacuoles fill, however. Even structures of cellular size, such as red cells, may pass through these channels by reason of their deformability. Though glaucoma following hemorrhage into the vitreous or anterior chamber may be produced by macrophages, red cell ghosts, and sickled red cells. Such cells become trapped in the inner portion of the meshwork. A number of studies have demonstrated that the formation of endothelial vacuoles to be pressure dependent, so that their number and size are reduced at low pressure and increased at high pressure. In the monkey eye, the frequency of giant vacuoles was found to be 1900 per millimeter length and 3200 per millimeter. Chipati proposed that the endothelial cells of the inner wall of Schlemm's canal have the ability to transfer aqueous in bulk by a cyclical pressure-dependent process involving the formation of vacuoles and transcellular channels. Whether this represents an active process involving a regulatory homeostatic mechanism or whether it is a passive phenomenon independent of energy remains to be elucidated. Whichever way this argument is resolved, it is accepted that aqueous enters the canal of Schlemm almost entirely by transcellular route, and only about 1% of the total conductance of the inner wall of the canal can be attributed to the non-vacuolar channels found in the narrow margin portions of endothelial cells. Outer wall. The endothelial cells of the outer wall of Schlemm's canal are longer, flatter, and smoother in outline than those on the trabecular side. The cells are joined by zonuli occludentis, show rare giant vacuoles on their luminal aspect and rest on a basal lamina which is thicker and more continuous than that on the trabecular side. Although morphologically it would seem that access of aqueous to the outer pericanalicular tissue must be limited. Fraser studies have demonstrated that a route exists. Collector channels. The collector channels arise at irregular intervals from the outer wall of the canal of Schlemm. They are 25 to 35 in number and drain into three interconnecting venous plexuses, the deep and mid-scleral and the episcleral venous plexuses. Up to 8 of these vessels drain directly into the episcleral venous plexus and are known as aqueous veins. They were first recognized by Asher, and their connection with the canal of Schlemm was confirmed by Ashton. With the slit lamp microscope, they may be seen subconjunctivally, either as clear vessels or showing a bilaminar flow pattern representing the presence of both blood and aqueous. The pressure relationships between these aqueous channels and the neighboring episcleral veins into which they drain were studied by Asher. They are found near the limbus, about 2 mm from it, most often inferonasally and often commencing in a hook-shaped bend where they emerge from the sclera. They may run a course of 1 to 10 mm before joining an episcleral vein. The collector channels are lined by vascular endothelium, similar to that of the outer wall of Schlemm's canal. They are relatively wide at their origin, 20 to 90 micrometer, but taper towards their anastomosis with the venous channels. No valves are present in the system. The channels are surrounded by a thin connective tissue. The deep scleral plexus is made up of fine branches of the anterior ciliary veins and drain into the mid-scleral plexus, which forms a large interconnecting intrascleral venous network at the limbus. This receives in addition blood from the ciliary venous plexus. Posteriorly, the intrascleral plexus drains into the episcleral plexus and thence towards the anterior ciliary veins. The episcleral venous plexus, in addition to its communication with the intrascleral plexus and the aqueous veins, receives blood from the conjunctival veins, draining the perilimbal conjunctiva. Intrascleral arteries of the limbus. It has long been known that an incomplete arterial circle accompanies the canal of Schlemm, derived from the superficial and deep terminal branches of the anterior ciliary arteries. Occasional arterioles pass through the lumen of canal separated only by their adventitia, while others lie in its external wall or breach the septa. No direct openings into the canal of Schlemm have ever been identified, and a role for this arterial system relating to aqueous drainage has not been accepted. The purpose of this rich limbal arterial supply is to provide nutrition to the tissues of this region. The arterioles show a fenestrated endothelial lining and a 1 to 2 layer medial coat. Innervation of the outflow apparatus. The innervation of the outflow apparatus derives from the supraciliary nerve plexus and the ciliary plexus in the region of the scleral spur. Both myelinated and non-myelinated nerve fibers have been demonstrated throughout the trabecular meshwork. Myelinated fibers are most commonly found towards the posterior attachment of the trabecular sheath. Nerve fibers have been observed within the core of the trabecular sheaths and crossing the intratrabecular spaces. Nerve endings are more plentiful in the region of the inner portion of pericanalicular zone. Various workers have identified fibers and terminals in the trabecular meshwork, and these have been studied more fully by electron microscopy. Nomura and Smeltzer reported nerve terminals chiefly in the posterior region of the trabecular meshwork, anterior to the insertion of the longitudinal ciliary muscle, and considered that about 1/3 were adrenergic. Ruskell in 1976 found unmyelinated nerve fibers throughout the trabecular meshwork and Schlemm's canal system, and most frequently in the pericanalicular tissue, with some fibers adjacent to the endothelial lining of Schlemm's canal. There was a large variation in the number of exons. Tripathi found fewer adrenergic terminals than Nomura and Smeltzer, and a more diffuse distribution in the meshwork. Various other workers have demonstrated nerves in the meshwork. Holland and colleagues in 1956 and 1957 believe them to be both somatic and autonomic. Lemos in 1962 has suggested that they were sensory. Tripathi and Tripathi in 1982 believe that both parasympathetic and adrenergic autonomic fibers and sensory fibers are represented. Although it is tempting to designate a role for such innervation in the homeostasis of intraocular pressure, no such function has been established. Nerve endings with structural characteristics of mechanoreceptors in the human scleral spur. The inner layers of mammalian eye are innervated by sensory nerves of trigeminal origin. Most of these fibers are type C. Numerous exons which stain positively for neurofilament proteins run forwards parallel to the muscle bundles in the meridional part of the ciliary muscle near its insertion into the scleral spur. The axons lie in the interstitial spaces between the muscle bundles. Solitary myelinated fibers, 2 to 3.5 micrometer wide, predominate and give rise to thin unmyelinated fibers which terminate between the muscle cells. Some of the transciliary myelinated fibers pass forwards beyond the anterior insertion of the ciliary muscle and give rise to a loose network of circumferentially oriented axons at the level of scleral spur. They are supplemented by myelinated fibers which have run forwards in the supraciliary space. These spur axons are found mainly at the inner aspect of the spur and they give branches to the meshwork. In places, the myelinated spur axons lose their myelin sheaths, branch profusely, and terminate in club-shaped nerve endings, which have the morphological features of mechanoreceptors found elsewhere in the body. Although there has been uncertainty about the existence of such specialized receptors in the past, they are probably identical to structures demonstrated by silver impregnation techniques and discussed as baroreceptors by Cruz in 1955 and Castro Carrera in 1967. They are found throughout the whole circumference of the scleral spur region and are supplied by terminals about 3 micrometer wide from myelinated axons. The receptors stain for neurofilament proteins and synaptophysin, a marker for synaptic vesicles. It should be noted that positive staining for synaptophysin is also exhibited by afferent terminals and probably associated with agranular vesicles. The intense staining of the axon terminals for neurofilament protein is in keeping with their myelinated status and they are assumed to be the afferent terminals of trigeminal neurons. In the monkey, 20% of neurons in the spur region are derived from the trigeminal region. And positive staining with one neurofilament antibody suggested that these might be fast-conducting type A sensory neurons. The club-shaped endings distributed regularly around the circumference of the scleral spur are larger and more densely arranged in older subjects, which suggests that they probably increase in size with age and also in chronic simple glaucoma. Morphologically, the endings contain abundant neurofilaments, 8 to 10 nanometer thick, granular and agranular vesicles, mitochondria and lamellated lysosome-like structures. These are similar to visceral mechanoreceptors in other parts of the body, such as the carotid sinus, aortic arch, respiratory system, arterial endocardium, and esophagus, and also in tissues such as skin, tendons, and joint capsules. The endings are invested with a continuous basal lamina but incompletely covered by a Schwann cell sheath, where the sheath is absent. The cell membranes of the endings are in contact with the neighboring connective tissue and in particular with the elastic fibers, which merge with the basal lamina and in some places are associated with specialized membrane densities. Contact between the nerve terminals and the extracellular connective tissue fibrils is characteristic of mechanoreceptor elsewhere. 3 potential roles have been proposed for these presumed mechanoreceptors. They may act as proprioceptive tendon organs for the ciliary muscle, whose longitudinal fibers insert into the scleral spur. They could also influence the contraction of myofibroblastic scleral spur cells, which have microtendon-like insertions into the elastic tissue of the scleral spur. Additionally, they could perform a baroreceptor function in response to changes in intraocular pressure. Physiological studies suggest that such structures exist in the eye since sensory discharges have been recorded in relation to the changes in ocular pressure. Some scientists suggested that the ciliary nerves of the cat eye contain afferent fibers which respond tonically within the normal range of intraocular pressure and originate from slowly adopting mechanoreceptors sensitive to changes in intraocular pressure. Figure 8.19. Scanning electron micrograph of the endothelial lining of Schlemm's canal. A. Original magnification 2000 times. B. Original magnification 10,000 times. Figure 8.20. Transmission electron micrograph of endothelial cells lining the trabecular wall of Schlemm's canal SC, showing various intracellular organelles, cytoplasmic projections P, extend from the cell into the subendothelial connective tissue region, probably to provide anchorage. Adjacent cell borders show simple end-to-end contact, overlap, and complex interdigitations. Arrows. M for mitochondria, ER is endoplasmic reticulum, G for Golgi apparatus. Original magnification is 27,000 times. Inset. Higher magnification of an intercellular contact zone between adjacent cells lining Schlemm's canal, showing a poorly defined tight junctions. Arrowheads. Original magnification 90,000 times. Figure 8.21 A. Survey electron micrograph of the endothelial lining of Schlemm's canal SC in a human eye, showing that the most of the vacuolar configurations V at this level are in direct communication arrows with the subendothelial extracellular spaces which contain aqueous humor in life. Original magnification 3970 times. B is electron micrograph of a vacuolar structure which at this level shows both basal and apical openings, thus constituting a transient vacuolar transcellular channel arrow. In this way, the fluid containing extracellular space on the basal aspect of the cell is temporarily connected with the lumen of Schlemm's canal SC, allowing bulk outflow of aqueous humor. And for indented nucleus of the cell, original magnification is 23,825 times. Figure 8.22. Electron micrograph of the basement membrane material BMM beneath the endothelial lining of Schlemm's canal. Note the irregular thickness of the basal lamina in places appearing as an interrupted thin band, small double arrows, while in other places it is loosely organized and consists of both amorphous and microfibrillar elements. The basement membrane is, however, interrupted across the basal invagination in the cell arrow that forms microvacuolar configurations V, which at times may contain some flocculent material. SC for Schlemm's canal. Original magnification is 44,000 times. Figure 8.23 A. Concept of the cyclical sequence of events in the formation of vacuolar transcellular channels and mechanism of bulk flow of aqueous humor across the endothelial barrier of Schlemm's canal. Initially, vacuoles are formed by a membranous depression or infolding of the basal aspect of the cell surface, stage 2. Progressive enlargement of this infolding leads to formation of a macrovascular structure, stages 3 and 4, then which eventually opens on the luminal aspect of the cell surface, that is stage 5, thus forming a transient vacuolar transcellular channel continuous arrow. Bulk flow of aqueous takes place down a pressure gradient, that is from the meshwork into the lumen of Schlemm's canal through such vacuolar transendothelial channels, which act as one-way valves. After a time, the basal infolding is occluded and the cell returns to its non-vacuolated stage, stage 1. On morphological and physiological grounds, this mechanism is postulated to be equally applicable to the bulk flow of cerebrospinal fluid from the subarachnoid space into the dural sinus across the mesothelial barrier of arachnoid villi. Figure B. A composite three-dimensional schematic rendering of the walls of Schlemm's canal SC and adjacent trabecular meshwork TM. The spindle-shaped endothelial cells lining the trabecular wall of Schlemm's canal are characterized by luminal bulges corresponding to unique macrovascular configurations V and nuclei N. The macrovascular configurations are formed by surface invaginations of the basal aspect of individual cells which gradually enlarge to open eventually on the apical aspect of the cell surface, thus forming a transcellular channels arrows for the bulk flow of aqueous humor down a pressure gradient. The endothelial lining of the trabecular wall is supported by a variable zone of cell-rich pericanalicular tissue, PT, below which lie the organized superimposed trabecular sheets having inter- and intratrabecular spaces that allow the flow of aqueous humor from the anterior chamber to the canal of Schlemm. The compact corneoscleral wall, CW, of Schlemm's canal is formed by lamellar arrangement of collagen and elastic tissue. Figure 8.24, the bases of the anterior segment. You can see here on the outermost aspect there are conjunctival vessels, then beneath that there is a vascular plexus in tenons fascia, then after that posterior to it, deeper to it, is anterior ciliary vessels, and even deeper to that is posterior ciliary artery. Figure 8.25, light micrograph of meridional section of trabecular meshwork tissue showing the location of an arteriolar twig A coursing through Schlemm's canal but separated from the latter by its adventitial wall. Original magnification is 1020 times. Inset transmission electron micrograph of an arteriolar twig revealing its continuous endothelial lining E and 1 to 2 layers of muscle cells M, an unmyelinated nerve bundle and with Schwann cell is present in the vicinity of the arteriole. Original magnification is 12,000 times. Figure 8.26a, innervation of the trabecular meshwork of the human arm. A is transmission electron micrograph showing several axons A surrounded by a Schwann cell within the core of trabecular sheet. TC for trabecular cell. Original magnification is 26,000 times. Figure 8.26b, diagrammatic representation of the distribution of nerve terminals, triangle, in the region of the trabecular meshwork and Schlemm's canal system. Figure 8.26c, whole mount preparation of a sector of the scleral spur of a 67-year-old donor with 0.5 millimeter circumferential length, immunostained with antibodies against neurofilament proteins. The anterior insertion of the ciliary muscle is situated beyond the top of individual micrographs, the trabecular meshwork beyond the bottom. Figure 8.26d. The club-shaped terminals derive from myelinated axons with a diameter of 3 to 3.5 micrometer. The axons, asterisked, lose their myelin sheath arrows and form distinctive half nodes of Ranvier 7,000 times. Figure 8.26 continued. E. Electron micrograph of a club-shaped terminal in the scleral spur, donor aged 38 years. The terminal has a length of approximately 25 micrometer and is densely surrounded by collagen C and elastic fibers E. The surface of the terminal is partly ensheathed by flat processes of Schwann cells S. Nonetheless, large parts of the cell membrane are still exposed directly to the extracellular fibrils, arrows, 6,300 times. Figure 8.26, Figure F. Tangential section of a scleral spur terminal, electron micrograph, 5,000 times, donor aged 56 years. The terminal is embedded in a meshwork of numerous circularly well elastic fibers E that are in close contact with the cell membrane of the terminal arrowheads. In addition, the terminal forms protrusions that surround larger parts of the nerve fibers, arrows. Thank you.